Now that we've been able to calculate the world coordinates of all the sensor rays that come from the rangefinder, we will introduce how to do this with matrices, and in particular how to use homogeneous transforms to dramatically simplify the code that you see here and make things much crisper mathematically. We are already using NumPy, which has a matrix format, and what you can do is you can define the rotation matrix as a matrix. The way we do this is we use the convention to use the character for the target coordinate frame first, so the W_R for rotation matrix, and then the little r because this is from the robot coordinate frame, and then we use the NP array to enter the rotation matrix. And in order to do this, you're using square brackets to enter individual rows. So now we have NP of cosine theta plus 1.57. And actually, let's make this more elegant and use minus sign, which is equivalent to what we have down there. And now to add the second row, we use another set of square brackets and put down the second row, and this one is sine of theta and NP of cosine of theta. Now the second piece we need for our matrix operation is the vector xw. Now let's write down an expression for xw, which is an NP array of xw and yw. Now I enclose those in square brackets as well because I want a column vector. If you leave out the innermost square brackets, you will get a row vector, which is not compatible with the matrix. And now what we can do is we can already write this down in matrix notation. So for that, we want to compute the range data. Let's call this vector D for data, for the lack of a better idea. And now we have our rotation matrix, and we multiply it with an NP array of xi and yi. And now we add the world coordinates. Now I've used the add symbol here because in NumPy the multiplication symbol like this is just an element-wise multiplication. What we need is a matrix multiplication, so we have to use the add symbol. And this row in the should be equivalent to what we've done down here. We are multiplying the rotation matrix with xi and yi, and then we add xw. So we can try this already, and instead of appending this, we should append the elements of D. So we grab the first entry of D, which is D0, and for YW we append the D1, which is the second entry. Now if we run this, this should already work. And this works. Now we have the same as before. This is not optimal yet. Let's do this with a homogeneous transform, which allows us to do this step here in just one single operation. Instead of having a matrix multiplication in addition for the translation, we can combine rotation and translation into a single operation. And for that, we copy this data structure here. And now this time we call it T for transform. And now in order to do that, we add a third dimension here, which is xw and yw. Now let's close these parentheses carefully. and we need to add the third dimension also below to make this a 3x3 matrix. Now we have, instead of a 2x2 rotation matrix, we have a 3x3 transformation matrix, which has this additional column at the end where we have XW and YW, and then we padded everything up with a 001 row at the bottom, and you will see how this works in a second. Now, when we replace the rotation matrix with the transformation matrix, we have a 3x3 matrix here, but we have only a 2x1 matrix here, so we have to add a dimension here as well. And the convention is to simply add another 1. Again, I have to enclose it into square brackets so that I have a proper column vector. And now we don't need to add XW at the end and can remove it also here. So you see, the homogeneous transform allows us to do everything in a single operation, a single matrix multiplication. And the result should be the exact same one. The third entry of the D vector is 1. But we don't need it. It is just carried forward to make the matrix multiplications compatible. Let's see if this works. Let's add this one here to make this complete. And of course, we need another square bracket here. Let's try again. And now the robot moves. And we have our map being drawn. All right, now we have understood the concept of homogeneous transforms, but we are still doing a for loop. We can now further optimize this and actually remove the for loop as well and do all of this in a single operation. So let's clean up a little bit here, remove everything we don't need. All right, now let's turn this entire thing into a single matrix operation. Now that we understand homogeneous transform, now we don't need the rotation matrix here either, but we will keep the transformation matrix. Now the first thing we have to do, we have to multiply all the ranges with all the angles. So in NumPy, doing this will give a 360 times 1 matrix, and this is a 360 times 1 matrix. The multiplication symbol is element wise, so this should just work. Now this is just the first component, so we want to do this row wise and create an NP array where we have this as the first row. In the second row we want to do the same thing but with sign of the angles. And now if we want to multiply this array with the D matrix, which is a 3x3 matrix, we need this to have 3 rows as well. So we pad this with 1s, and here you will need some NumPy trickery. When you create an array of 1s, you can provide the dimensions. So now we have the right dimension here, and we will get a 3 by 360 matrix that is made of this row, that row, and this row, each 360 elements. Now we can do our matrix multiplication. So let's copy this from here, but this time we multiply directly with the xi array. Now we have a 3 by 3 matrix, we multiply with a 3 by 360 matrix, so we get a 3 by 360 matrix with all the entries that we need. We can safely now delete all of this here because this is all done. And now we want to plot the entire row of this D matrix. So we take the first row and the second row. So for those of you who have been wondering about the error, every now and then there is a problem with the matrix multiplication because there's an invalid value. And indeed, the for loop did more than just doing the matrix operations. We need to clean the ranges of infinite values, and you can do this by turning the ranges into an NP array, and then you can say ranges of where ranges are equal to NP inf are 0, and this should clean them from all infinity values. And here you go. Now you have everything that we've done in a for loop in one simple matrix operation. So for those of you who have been wondering about the error, every now and then there is a problem with the matrix multiplication because there's an invalid value. And indeed, the for loop did more than just doing the matrix operations. We need to clean the ranges of infinite values, and you can do this by turning the ranges into an NP array, and then you can say ranges of where ranges are equal to NP inf are 0, and this should clean them from all infinity values. And here you go. Now you have everything that we've done in a for loop in one simple matrix operation.